Hi everybody. We're going to move along this week, still considering friction, but now moving along to like hills and inclines. So today's goal is to simply identify what happens to forces on an incline and denote whether there's friction present or not in certain situations. So let's just quickly review using the simulation that we were using last week. I just put a heel on it this time, but let's review something about an object at rest on a flat surface. I'll click on force vectors. Recall that if an object is at rest on a flat surface, that there is no friction acting on it, all right, because it's not sliding or trying to slide right now. And just another old review, but important, is that the only forces present are the normal force and weight, and they are totally balanced with each other. So if this crate weighed 980 newtons, the normal force would also be that. But now we're going to move to putting this thing on a hill. So I'm going to apply a force just to push it up on the hill, and that was too hard, so I'm going to reset that. There, we got a wall up there now. I just want to get it on the hill. Oh, hill's too high. Hold on. Let's put it on a hill that it doesn't slide. There we go. Alright, so it's not much of a hill, but it's a hill. I'm going to get rid of the force vectors now because we'll do our own diagram with that. But here's the deal. Once we are now on a hill, the object is still at rest. But the biggest deal right now is that there is friction present. So why wasn't there when it was at rest on a flat surface, but there is now? Remember, the reason why there wasn't friction on a flat surface at rest is because the object was not sliding or trying to slide. Once you put it on a hill, it is trying to slide. I could prove that by gradually raising the hill, and if the angle is too steep, then that hill causes the object to possibly slide. Alright, so it wants to slide, it's just that maybe the angle isn't high enough, causing some sliding forces, which we'll identify here in a second. So, biggest thing to start, on a hill there is friction. If it's not sliding, it's static, but it at least is trying to slide in that case. So we're going to diagram a object at rest on a hill to start today. So let's start with our free body diagram like always. What force is always present? Weight, right? Force due to gravity. It's always directly down, and that's still true. But something a little different is going to happen with it now. But I will label that as F sub g. And by the way, just generically for right now, the angle of inclination is going to be referred to as theta. Now, the next force, that's the one that's still familiar with us, hopefully, that we're going to draw is the normal force. This object's not falling through the incline. Now, this is where it starts to get a little bit different from what we're familiar with, though. On a flat surface, normal force was always directly up. If you remember way back to when we first started the most introductory stuff to forces, when we defined normal force, it was defined as an upward perpendicular to the surface force that basically from a surface pushes back on something. Well, since we've always been on a flat surface up to this point, perpendicularly up was actually always straight up, but no longer. Now the normal force is not going to be straight directly up, but it will still be perpendicularly up from the surface. So it's still what causes the box to not fall through the surface, but it's no longer equal to 100% of the weight. So if this was a 100 Newton box in weight, my normal force would no longer be 100 newtons. What would it be? Well, that's what we got to figure out. Right? But let me put one more force on there, what we're familiar with, what was causing it to try to slide even though it's not. Opposing the sliding even though it's not, excuse me, if it's at rest. is the frictional static force, which pulls up the incline. Why does it go up the incline? Because the object wants to slide down it, right? So friction's not letting it, so it's up. And actually, I'm going to redraw that just a little hint smaller for reasons I'll talk about in a moment. And it is static because it's not sliding, but it's trying to. Alright, now here's the biggest difference dealing with the incline. And that is what happens to gravity, the force due to gravity. It's as if it does two things at once you're on a hill or an incline. And we break it up into components. And we actually draw those components in what we call head to tail, because they're vector components. Remember a couple of weeks ago we went over that? And these two components we call FG perpendicular and FG parallel. You should remember, hopefully, from geometry that FG perpendicular, this symbol's perpendicular, and this symbol down here is parallel, two lines. Why do we call it that? Well, it's pretty simple. This one's perpendicular into the incline, this one's parallel down the incline. These are what we call the two components of the weight. Okay, this doesn't happen on a flat surface. And we're going to derive formulas through SOHCAHTOA. One other very important thing we do with inclines, and you've never done this probably in math for any reason because you never ran into a reason, but like always, physics applies the math and applies it to very different scenarios that you're used to probably. What we like to do for inclines is tilt the XY axis. We're actually going to make the x-axis, I'm just going to overlay a dotted line, the incline itself. And we're allowed to do that because direction's always arbitrary. The only thing that has to be true if we do that is that the y-axis has to be perpendicular to it. So the y-axis will lay right along here perpendicular. And really that way when we apply Newton's second law a little bit later this week, we could still do it axis by axis because the majority of our forces are on an axis. Now that we've tilted the XY axis to fit the incline, the only force that we drew in that wasn't right on the axis was weight. So we broke it up into its components, FG perpendicular, FG parallel. And my diagram is not 100% to scale, but that's okay. The direction of where everything's pointing is what matters the most. Okay? So, these components, what are they and what do they do? They're pieces of overall gravity. Gravity overall is still down, but the incline being at an angle in the way causes gravity to do two things at once. This component, the perpendicular component of gravity, wants to push you into the incline. Alright? It wants to force you into the incline. And so not all of your weight is going into the incline. So normal force is no longer, this is super important, no longer equal to all your weight. It's only equal to the perpendicular component, because we can see in our diagram that's what the normal force is opposite of. It's not opposite of the overall weight vector right here. Alright? So a very important thing that we're going to list for inclines is now the normal force doesn't equal weight, it equals just this component of weight. Super, super important, okay, moving forward, because we were used to something else on a flat surface. Now this parallel component of the weight, you notice it points down the incline. This is the component or piece of the overall weight that wants to pull us down the incline. That's why we're trying to move, and that's why there's friction. And if we're not moving because of it, it's static friction. If we did start to slide, that would change to kinetic friction. So we need to come up with two basic formulas for these two components of weight. And I'm going to draw in the angle here as well. I'm going to prove this fact in a moment on another video very quickly. But for now, take my word for it. Whatever the angle of inclination is, here, theta, is also always going to be the same angle in this head-to-tail component diagram drawn with weight. All right. So if this angle is 30 degrees, this is always 30 degrees. Again, I'll prove that in a moment in a secondary video if you'd like to watch it. All right. So if I have a reference angle theta, and these are sides to a right triangle because I drew them in head to tail like we discussed with components several weeks ago, I could simply use SOHCAHTOA to figure out the formulas for perpendicular and parallel components of the weight. So FG perpendicular, now let's start it like this actually. I'll come down here and do it, keeping that part of the diagram. Remember, the reference angle is right here in the kind of like weird arranged triangle. So that means the weight, the red vector, is the hypotenuse. The perpendicular component of the weight is the adjacent side, and the parallel component is the opposite. So if we use cosine theta, that's going to be equal to, from SOHCAHTOA, adjacent over hypotenuse, or in other real words, FG perpendicular over the hypotenuse, the overall weight. Now usually we use this formula to solve for FG perpendicular, so I'll isolate that by multiplying weight over to the other side. And another secondary substitution we can make, it's the same formula, but if needed we could say weight is equal to mg. I could sub that in. You should remember why, because FG equals mg from a long time ago. So both of these formulas are the same, just one of them has mg substituted in for weight. Either could help us find the perpendicular component of the overall weight. And so when we do find this, and we'll do an actual example here in a second, that finds out how hard our weight is pushing into the incline. So if this thing weighed 100 newtons, this is only going to be a fraction of that 100 because not all of my weight is pushing directly into the incline, right? Part of it is trying to pull me down the incline. So now we set up that formula. We could say that the sine of the angle theta is equal to the opposite side, or FG parallel component, over the overall weight, the hypotenuse side. And again, we usually solve this for FG parallel because that's what we want to know, by multiplying weight over to the other side. Since we're using sines and cosines, when you actually calculate in your calculator, make sure you're in degree mode. And I'm again going to show this formula as the same one, but I could, for overall weight, I could sub in m times little g and get that version of it as well. Okay. And this is the amount of your weight that is trying to pull you down the incline that the friction must oppose on the tilted x-axis. Okay, and don't forget, what I already mentioned above here, I'm going to circle it again, that on an incline, in a situation like this or similar, the normal force equals the perpendicular component of the weight, not the overall weight anymore. Alright, so that's the newest stuff, and through the coming days we'll add to some of this, but today's example is just going to be simply plugging into those formulas and making sure your calculator is in degree mode. So let's all go to example 5 on page 133, and I'm not going to redraw a free body diagram. I'm just going to flip back to the one I have because I drew a generic one, but it could apply to it. It says in example problem 5 on page 133, the components of weight for an object on an incline. A crate weighing 562 newtons. So its weight, F sub g, is 562 562 newtons. It's resting on an incline that has an angle of 30 degrees. Find the components of the weight that are parallel and perpendicular to the plane. So this is just plug and chug. But while it's important that you know how to do this, it's most important that you know what they represent. So let's find them and talk about that. So like using the formulas we just derived on the prior page, FG perpendicular equals FG cosine theta, and that's 562 times the cosine of 30 degrees. Again, super important your calculators in degree mode. So running those numbers right now, and I get about 486.7 newtons. Again, let's realize what this number really is. Since it's the perpendicular component of the weight, that's how much of the weight is pushing this crate into the incline. Okay? Into the incline. We also want to find the parallel component. FG parallel is equal to the overall weight, which is 562, times the sine of the angle of inclination. So, again, just plug in the numbers. This should be very simple. Plug it in, run them, and we get exactly 281 newtons. This is the amount of weight that is parallel down the incline, or in other words, 281 newtons of the overall weight is trying to pull you down. 486.7 is pushing you in. And although it didn't ask, I still want to point it out. If this is how much is pushing you into the incline, the perpendicular component, that is what the normal force of the incline is also pushing back on you with. And speaking of that, let's go back to the general diagram. As always, you don't have to draw a free body diagram for a problem on a test or quiz unless I ask. But this is very important because on a test or quiz, if I do ask you to draw one, it is essential that this vector looks pretty perpendicular. I know mine's not perfect. I don't expect anybody freehand to be perfect, but this better look like it's perpendicular into the incline. This better look pretty parallel to the incline. See how here's the incline, parallel. We all know what that means. It should look to the naked eye pretty parallel. Overall weight should always look directly down. Normal force should be perpendicularly up from the surface, not straight up. If I asked you to draw this on a test or a quiz and you do normal force straight up, that would be incorrect. Force of friction, in this case static, is parallel up the incline. Alright, it's very important. If I ask you to draw this, you don't draw it messy. Everything should look pretty good, even drawn freehand. Okay? Alright, so for now, that's all there is to an incline. Again, I'm going to post a second video proving that this angle equals this angle through some basic geometry. But for now, I'll take my word for it. Your homework today that will be posted along on an assignment on Classroom is just going to be 3 hopefully pretty basic problems. On page 133, I'd like you to do 34, 35, and 36. And don't forget, if the weight's not given, the mass will be, and of course we can make that mg sine of theta or mg cosine of theta if needed. Okay? And we'll continue along with adding more to this stuff later in the week.